Okay, let us proceed with part 3 of lecture 16. So we are going to have one example, okay, in which we are given a transfer function of Hs given by k, a constant, s plus z1 divided by s times s plus p1. Okay, so please ignore these terms here. It's nothing. There is no effect of these terms here, yeah? Right, so again, if we base on this HS, there are 4 terms to be considered. We have a constant of k, we have a 0 at z1, we have a real pole at p1, and we have pole at origin, yeah? Okay, so as what I've mentioned just now, we have to take, we have to use 3 steps in order to plot the Bode diagram for the HS. The first step is to write the HS in a correct form. Okay, so what I did here is this is first step now, where we have the k, we have to take out the z1. So we have to write this as 1 plus s over z1. So s still there, and we have to take out the p1. Yeah, so we're going to have p1, 1 plus s over p1. So end up we are going to have a new constant, which is k of z1 divided by p1. Okay, and the rest will follow 1 plus s over z1, s, and 1 plus s over p1. Okay, this is the first step, which is to write the hs or hj omega in a correct form. Yeah. Okay. So let us proceed with the second step, which is to actually sketch the individual plot for both the amplitude and the phase. So we start with the amplitude plot first. So what I did here is we give a value for the previous constant. Yeah, so we have k z1 over p1 is equals to set of 10. Z1 is 0.1 radian per second and p1 is 5 radian per second. So these are the given value for the constant, for the zeros of Z1, and for the pole at P1, yeah? Okay, so looking back at the previous equation, so we are going to have 4 different plots: a constant, a real zero, pole at origin, and the real pole at P1, yeah? Okay, so let's sketch the individual plots of this. So what we have here, the dotted line, the orange dotted line here is the sketch for 20 log offset of 10. So 20 log offset of 10 will give us 10 dB. Yeah, 10 dB. Okay, so what we did here is we write all of these in terms of the dB scale. Yeah, dB scale. So we are supposed to get all of these shall be now considered to be 20 log of this term plus 20 log of this minus 20 log of s minus 20 log of pole value. Yeah. Okay. So back to this, we are going to have a constant of 10 dB. Next one is for the real zero at 0.1. Yeah, we have a zeros of 0.1. So as what we have learned in the previous slides, yeah, for 0.1, for a frequency lower than 0.1, the amplitude is 0 dB. And for higher frequency, we are going to have a slope of positive 20 dB per decade. Yeah, so we're going to have 0 dB. And for higher frequencies value, is bigger than 0.1, there should be a slope of positive 20 dB per decade. Okay. Okay, so the pink dotted lines here is a plot for real zero. Okay, plot for real zero. The third one is the plot for pole at origin. Yeah, pole at origin. So for the pole at origin, as what we have learned in the previous slide, there should be a slope of negative 20 dB per decade, and the slope need to pass through the frequency of 1. So the blue dotted line here is the plot for for the pole at the origin, passing through the frequency of 1 here. Okay, and because there is two decades here, yeah, 0.01 to 1 frequency, there are two decades. So that to maintain the slope of negative 20 dB per decade, the blue dotted line need to pass through 40 dB, such that the slope of this line will be negative 20 dB per decade. Yeah, because this is 40 dB, the decade is 2, so 40 divided by 2 will be negative 20 dB per decade. Okay, so the blue dotted line is a plot for the pole at origin, and finally is for the plot of real pole at 5. So for the real pole at 5, we are going to have 0 dB up to 5, and after that, for a bigger value of frequencies bigger than 5, we are going to have a slope of negative 20 dB per decade. So the green dotted line, yeah, is this plot for the real pole at 5. Okay, so all of these are based on the individual plot that we have learned from the previous slides. Yeah. So our task now is to actually combine them. So what should be the pattern of your amplitude plot? So to get the amplitude plot for this, okay, so you have to start from omega equal to 0.01. So looking at this, we can see that there is a slope here of negative 20 dB per decade, starts at 40 dB. But looking at this, there is a constant of 10 dB. So the effect of this constant is basically it will actually uh, increase the amplitude. So somehow it is look like the amplitude shifting. Yeah, the amplitude shifting. We are shifting the amplitude of this slope to a 50. Yeah, to a 50. So that's why we're going to start the slope at 50 dB because of the effect of this 10 dB increment. So at 50 dB, we're going to have a slope of negative 20 dB per decade, which follows the blue line sketch. Yeah, so that should be the line, a solid line, a black solid line is the actual plot. So negative 20 dB per decade up to 0.1. So why it stop at 0.1? Because at 0.1, we notice that there are two slopes. The slopes are blue, which is negative 20 dB per decade. And the second slope is the pink color, which is positive 20 dB per decade. So at 0.1, starting at 0.1, there are two plots, or there are two slopes, the blue and the pink. And both are having different sign, negative 20, positive 20. So the net value of the slope will be 0. Yeah, because when we add them together, the net slope will be 0. So that is why we are going to have a slope of 0 dB per decade, and it will continue as long as the two slopes there remains the pattern. Yeah, so it can be see that these two slopes will continue from 0.1 to 5. Yeah, 0.1 to 5, and at 5 we can now see that okay. So at 5 there are three slopes now. We are the slope of the pink color of positive 20, the slope of the green color, which is negative 20 dB per decade, and the slope of blue color of negative 20 dB per decade. So when we add these three slopes together, we are going to have a net slope of negative 20 dB per decade. That is why from 5 onwards, the slope will be now becomes negative 20 dB per decade. So this is the addition of the individual plots that lead to the formation of this final solid line. Yeah. Okay. Hopefully you are clear about this. So let's have a look at the phase plot. Yeah. So for the phase plot, we have 4 plots, individual plot just now, constant. So for a constant, we know that the plot will be 0 degrees, constant. For a real zeros, yeah, real zeros, we are going to have the pink plot, yeah, the pink plot, where we have at 0.1, there should be 45 degrees angle. 1 decade smaller, which is 0.01, will be 0 degrees. and 1 decade higher, which is at 1, the phase will be positive 90 degrees. So we can connect these 3 points here at 0, 45 degrees, and 90 degrees. When we connect this line, we are going to have a slope of 45 degrees per decade positive. Yeah. Okay, this is the pink color is the plot for the phase angle for the real zeros at 0.1. Okay, and for the pole at origin, so we have learned for the pole at origin, the phase is negative 90 degrees, a constant value, yeah? So the orange color dotted line is the plot for the phase, the plot for the phase for the real, for the pole at origin, yeah? Pole at origin. Okay, and then for the real pole at 5, we can say that for smaller frequency, yeah, we know that at 5, the angle will be negative 45 degrees. Yeah, at 5, angle will be negative 45 degrees. 1 decade smaller, which is at 0.5, the angle is 0. And 1 decade higher, which is at 50, the angle is negative 90 degrees. Yeah, this is for the pole, real pole at 5. Yeah. So when we connect this line, 0.5 will be having 0 degrees, 5 will be having 45 degrees, negative 45 degrees, and 50 will be negative 90 degrees. When we connect this line, you're going to have a slope for a phase angle plot for a real pole at 5. Okay, so we are now going to sum these plots together. Okay, so we know that the starting point of this phase plot should be at negative 90 degrees because somehow it is similar to the concept of amplitude shifting. Yeah, we have a constant of negative 90 degrees. So we're going to start here. Yeah, negative 90. So we start at negative 90. Yeah, we're going to have a constant value up to 0.01. So at 0.01 onwards, we're going to have a slope which follows the slope of this pink color of 45 degrees per decade, and it will stop at 0.5 because at 0.5 we're going to have two slopes, the pink color and the green color. The pink color is 45 degrees positive per decade, and green color is negative 45 degrees per decade. So when we add this together, we are going to have a net slope of 0 degrees per decade. So that's why we're going to have a constant. And this will end at 1 because at 1, we can say that there should be only a single slope of negative 45 degrees per decade because the pink color has now become a constant. Okay, so from 1 onwards, yeah, from the frequency of 1 onwards, the phase plot will be a slope, will be having a slope of negative 45 degrees per decade until it reach 50, and afterwards we are going to have a constant of negative 90 degrees. Okay, so the solid black line here is the plot for the phase, yeah, plot for the phase. Okay, so I hope you understand about this issue. So in case if you have you have any questions related to the amplitude plot and the phase plot for this example, don't hesitate, please contact me. Okay, so these are the exercises that the answers for these are given at the back of this. Yeah, so you can just test this on your own. Yeah, because I provide to you the slide in PowerPoint. So in PowerPoint, I did it one by one. Yeah, in terms of the plotting, so that you're going to understand this better. Okay, so let's have a look at these exercises. There are 4 exercises given here. So I have written the HS, all of them in the correct form. Yeah, for instance, for the first case here, 10s over s plus 1 over s plus 100. So what I did is that I have 10s and I take out 100. So we're going to have 100 here and 1 plus s and 1 plus s over 100. So end up, we're going to have 0.1 s over 1 plus s, 1 plus s over 100. So for this example, there are 4 terms, a constant of 0.1, zeros at origin, pole at 1, pole at 100. The same things happen for the second example. Okay, the same things applied. I write this in the correct form. I take 10. Yeah, I take 100 outside, so I have 10 over 100. So 1 plus s, 1 plus 100. So we're going to have 0.1, 1 plus s, 1 plus s over 100. So based on this HS, there are four terms: a constant of 0.1, zeros at 1, pole at origin, pole at 100. And the rest follows. Yeah, so you can have a look at the rest of this question. There are two more questions here, right? So the answer for these exercises have been given in the next slides. Yeah, you can try to understand how I plot these transfer functions. Okay. All right. So I think that's all for the lecture 16. I hope you understand well on the Bode diagram. Yeah, because this understanding on the Bode diagram is very important for us to proceed with lecture 17 and lecture 18 after this. Yeah. Okay, so first of all, you need to understand lecture 16 on how to sketch the Bode plot or how to draw the Bode plot. Okay, so once you have understand this Bode diagram, then only we can proceed with lecture 17 and lecture 18. Yeah. Okay, thank you very much. So we're going to meet you again lecture 17. Thank you very much.